So we're looking at our next set of organization for different types of data. So we previously looked at qualitative data and how we can organize that. We looked at um, pie charts, bar charts, and that was pretty much the extent of what we looked at as far as qualitative data goes. The Again, don't forget we did talk about frequency, which means you just count how many times a given value occurs. Relative frequency is basically the percentage of that, how many times that particular data point occurs. And we're going to carry some of that over into quantitative. Now, one of the things I mentioned in the last set of notes was with a bar chart, your bars do not touch one another. We're going to talk about, because I said that if they do touch, it becomes a histogram. And we're going to talk about histograms here in the next uh, set here when we talk about quantitative data. So to organize quantitative data, you want to group it into classes. And this will be known as categories, or, well, I did not mean to use a pink marker on there, but it's also known as categories or bins. And then we can treat those classes as distinct values of qualitative data. So there's a couple of things that you might want to keep in mind when we start looking at organizing qualitative data, or quantitative data rather. And you can see that right here with, I've labeled them as 3 common sense but important guidelines for grouping quantitative data. So the first one, you want the number of classes should be small enough to provide an effective summary, but large enough that you can display the relative characteristics of the data. A rule of thumb is that the number of classes should be somewhere between 5 and 20. The second one is that each observation must belong to one and only one class. That is, that each observation should belong to some class and no observation should be in multiple classes. Then the third one, whenever feasible, all classes should have the same width. Roughly speaking, this guideline means that if possible, all classes should cover the same number of possible values. And for just right now, those are just 3 guidelines. Right now, they probably don't make any sense to you. You keep hearing this word. We're talking about classes and width of a class, and right now, a lot of that doesn't make sense. As we go through these notes, hopefully that will make more sense, and you can refer back to these later on in your own time and see, okay, now I do understand what's going on. The first thing that we're going to look at is what we call single value grouping. And single value grouping is exactly what it sounds like. We're grouping things into single values. We can, let me get my highlighter here. Single value grouping is particularly suitable for discrete data in which there are only a small number of distinct values. So remember, discrete means something that we can count. Continuous is something that we measure. So if it's something that we can count, we can use single value grouping, and we can demonstrate that through example with this first example 1. It says the Television Bureau of Advertising publishes information on television ownership. The table provides the number of TV sets per household for 50 randomly selected households. Use single value grouping to organize these data into frequency and relative frequency distributions. So again, frequency is the count of the values, and relative frequency is the count divided by the total number of observations. So for our particular data set right here, we have 50 observations total, and that's going to come into play when we do our relative frequency table. So what I want to focus on right now is just what's on the left-hand side of our screen, which is the count. Each one of these data points represents how many TVs are in a household. So the first person that they questioned had 1 TV. The second person had 1. The third had 1. The fourth had 2 TVs in their house. And we could keep going on through the list. Rather than sit here and me count out and make a table of all 50 values and start tallying them up as we go, I've gone ahead and done that, and I've created this second table that you see on the right hand side of the screen. So just keep in mind, separate these 2 things in your mind. The left hand side is the data that was collected from the 50 randomly selected households, and that table shows the number of TVs per household. The right hand side um, is where I tried to save a lot of time on the video by going ahead and computing these values and putting it into our notes. So the first column is the single value grouping, and that's our number of TVs. You can see from our data set on the left, we never exceeded 6 TVs in any one household. So our single value grouping, we used 0, 1, 2, 3, 4, 5, and 6. 6 was our maximum value, 0 was our minimum value. We did have one family that had no TV in their home. So then the middle column is the frequency. So if I look how many people had 0 TVs in their home, like we just said a second ago, there's just one family that had 0 TVs in their home. So we get a frequency of 1. If we go through and we count up all the individual families that had 1 TV in their household, we can go through and we can start circling these values. And if we tally them up, we would get 16. Again, we could do it for how many families have 2 TVs in their home. Again, go through, circle all the 2's, and we would count them up and we would get 14. And we could keep going through that. You can use whatever method you want to when you're presented with a table like this one. It might be easier to just maybe cross through each one as you go to make sure you don't count some data point more than one time. And then also at the end, you might see that you skipped the data point by accident. So if we go down through the list, 3, there's 12 households with 3 TVs. There's 3 households with 4 TVs, 2 households with 5, 2 households with 6, and that's all of the frequency values. We've counted them all up. If we add this up, we should get not 40, we should get 50. 1, 16 is 17, plus 14 is 31, plus 12 is 43, 46, 48, 50. So it all does add up. And then when we add up our relative values, it should be 1 or somewhere really, really, really close to 1. Again, that if we think back to our example from yesterday or from the previous video, our relative frequency values added up to something slightly greater than 1, and that was just due to rounding errors. And you're going to see that from time to time. So single value grouping, pretty straightforward. We just took all the individual values. If we listed all of them out, 0, 1, 2, 3, 4, 5, 6, that was it. That's the limit of our values. Then we just tally them all up, and there's our single value grouping. That's probably pretty straightforward and easy to understand. But then the next grouping type is something that might be new to a few of you. It might be something you're not used to, and it's going to take practice. You guys will get this, I promise. So the second type of method for organizing quantitative data is called limit grouping. And limit grouping is we express our data points in a range of values. For example, let's say we looked at the height of, it's probably not the best example. Yeah, we could use height. Let's say we looked at the height of everybody in our classroom. I'm going to pick on Tylen because I believe she may be the shortest one. She's pushing right at 5 feet. So that'll be our minimum value. And then if we included myself, then we would go all the way up to 6 feet 8 inches. So we could have grouping classes. We could say we could go from 5 feet to maybe 5'4", and then we could go 5'5" to 5'8", 5'9" to 6 feet tall. Then we could go 6'1" to 6'4". Is that what I want to do? And then we could go 6'5" to 6'8", and then 6'9" to 7 feet tall. But that just kind of gives you an idea of what we're talking about. We're setting up a range, and then so we would tally up how many people fall within each range, and that would be our frequency, and then we could come up with our frequency distribution. The example that I used here in the notes, again, I've given us our table of values. I've gone ahead and created the table on the right. We're not going to go through the time that it would take for me to sit here in a video when you guys sit and watch me count everything up and do this. So I've already saved that time by computing the table on the right. So the table right now that we have on the left, it displays the number of days to maturity for 40 short-term investments. This data comes from Barron's Magazine. We want to use limit grouping with grouping by tens to organize these data into frequency and relative frequency distributions. So grouping by tens, we would say we would have a range of 10 possible values in each limit grouping set, and then we would count up all the values that fall within that particular range, move on to the next range, which would contain 10 more values, count those up, and we would go on and on and on until we exhaust all of our data points. So if we look through our table of data that we're provided, let's see, there's 36. That appears to be the smallest value right now. 36, that is the smallest value. Then if we go through and we look for our largest value, it would definitely be 99. I don't see any 3-digit values, so 99 would have to be the largest in there. So 36 is the smallest, 99 is the largest, and we want to divide this up into groups of 10. So if I don't want to start right at 36, because then it would be 36 to 45, 46, and we could keep going on and on and on. But our value, we wouldn't have, our last group was what I'm trying to get at, would not have a width of 10. So we need to come up with a range that would allow us to have equal size limit groups. And you can see in our table we started at 30 to 39. There's 10 values right there, 30, 31, 32, 33, all the way up to 39. And we do have several values that fall within that range. Specifically, we have 3 values that fall within that range of 30 to 39. Then we would jump to our next limit group class, which is 40 to 49. We would count up all the values that fall within 40 to 49, and we only had 1. Then we would jump to the next class, 50 to 59. We go back to our table, count all the values that fall between 50 and 59, and we get 8. And then we would just keep doing that until we get all the way up to our last class, which contains the groups, or the values 90 to 99. Count those up, we get 4, and we have created our frequency table. The right-hand column is relative frequency. We have 40 investments. Our frequency value totals up to 40 if we add that column. So then we would take each one of those frequency values, divide by 40, and that's where we get our relative frequency. So 0.075 all the way down to 0.10. So limit grouping, we just divide our data set into equal size classes, a range of values, and then we can come up with this table on the right hand side of the screen. And here in the green box you have definitions used in limit grouping. Lower class limit, so that's the smallest value. Upper class limit is the largest value that can go in a class. The width, the class width, is the difference between the lower limit of a class and the lower limit of the next higher class. So you can see in the table above here, my first class, the lowest value in that is 30. The lowest value in the next higher class is 40. 40 minus 30 is 10. And we can compare that all the way down. 50 minus 40 is 10. 60 minus 50 is 10. 70 minus 60. 80 minus 70. 90 minus 80. So all of our widths in this particular table meet the criteria that we specified earlier of being a width of 10. And then the class mark is the average of the two class limits of a class. So if I wanted to find the limit or the class mark of 30 to 39, I would add them together. I would get 69, divide that by 2, and I get 34.5. So that's the class mark. And I actually broke this down. If we consider the class 50 to 59 in example 2, lower limit is 50, upper limit is 59. The width is 60 minus 50. That should be equals 10, not minus 10. And then the mark is 50 plus 59 divided by 2. It's 54 and a half. Really, you're not going to see this a whole lot, these different groupings, or these analyses rather. What I've highlighted right here, the lower limit, upper limit, the width, and the mark. It's not going to really show up a whole lot more beyond this section of notes. But it still is helpful to know, because in other types of statistical analysis that you may encounter, it might be important to have that information. A third method of grouping is called cut point grouping, and it's really kind of similar to the limit class grouping that we just looked at. But with cut point, I don't know how to describe the primary difference. I've got dogs barking again. The best way to describe the primary difference between the two, when you look at limit grouping and cut point grouping, um, the similarities are: with limit grouping, each class consists of a range of values. You have the same thing with cut point grouping. Um, it's really This is probably more useful when you have continuous variables as opposed to discrete values. With that previous example, in example 2, you can see we had discrete values. We're looking at a count on how many days to maturity. So we're not doing a measurement, we're actually doing a count. With cut point grouping, you're looking at continuous variables, something that you can measure. And it might be clearer if we look at example 3, where we have the U.S. National Center for Health Statistics publishes data on weights and heights by age and sex. And they publish that in a document called Vital and Health Statistics. The weights that are shown in this particular table on the left-hand side of the screen are, to the nearest tenth of a pound, are obtained from a sample of 18 to 24-year-old males. So we know every value in this table is represented by some 18 to 24-year-old male. We want to use cut point grouping to organize these data into frequency and relative frequency distributions, just like we've been doing. We want to use a class width of 20 and a first cut point of 120. So if we know that our first class cut point is 120, and we want a width of 20, 120 plus 20 is 140. So that's where we get this 120 to under 140 pounds. Then we would jump 140 pounds up to 160 pounds. Then we go from 160 pounds to 180, and so on down through the list. With this table, we go about the counting the same as we did with the limit grouping, with a discrete variable, with a continuous variable. Now we're just looking for, in this first group, anybody that weighs 120 pounds up to, but not including 140 pounds. So here's 1, 2, 3, and that's it. We have 3 values that are between 120 up to and not including 140 pounds, and that's indicated right here. We have a frequency of 3. Then we would jump to the next cut point group, which is 140 pounds up to but not including 160. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And again, that's the same count we have right here. We could go down through the entire list. We'll generate our frequency values, and then we would also have our relative frequency by adding up the total in the frequency column. 3 plus 9 is 12, plus 14 is 26, plus 7 is 33, plus 3 is 36, plus 1 is 37. So we have 37 data points in this particular table, and so we would take 3 divided by 37, and that gives us our relative frequency. go on down the list, divide everything by 37. You get our relative frequencies. I hope this makes sense so far. When we start doing more computations, I hope that things really work out better. I've provided you with a table here to kind of give you an idea of what the best grouping method is to use and when to use it. So for single value grouping, you use that with discrete data in which there are only a small number of distinct values. So that goes back to the TV. Uh, our distinct values were 0, 1, 2, 3, 4, 5, and 6. That was a small number of very small distinct values, so it was easy to work with. Limit grouping, when the data is expressed as whole numbers and there are too many distinct values to employ single value grouping. So that was the number of days to maturity for those short-term investments. We could express the number of days as a whole number, and there's a very large range for all the number of days that could be expressed, so we used limit grouping. And then with cut point grouping, it's used when the data is continuous and can be expressed with decimals or fractions, whatever the case might be. So those are when you would want to use those three different types of grouping. It's going to be helpful when you start looking at the homework problems to know the difference between those three types and when to employ them. I think on most of the questions in the homework, I tell you which specific type of grouping to use. There may be one or two where you have to come up with the best method of grouping. Choosing the classes is going to be one of those subjective things. Unless you're specifically told otherwise, choose the size or the width of the class that suits you best. In the first couple of examples, it was specified. I think on that last one, we had a cut point group width of 20 pounds. So we went from 120 up to, but not including 140. If you felt it better to use 10 pounds as your cut point groups, you could have gone 120 up to 130, 130 to 140, and so on. It's going to be one of those situations where you use your better judgment and you present the data as you see best fit. Like I said, unless you're told which size width or which size class to use, then you do what you think is best. Histograms, this is where we talk about the difference between bar graphs and histograms. A histogram is a way to represent quantitative data. It's very similar to bar graphs, except what we have is scenarios where the bars are touching one another. And this comes in to play later on when we look at shapes of graphs and shapes of the uniformity of the data, how it's distributed. We're going to start talking about normal distribution, whether it's right skewed, left skewed, unimodal, bimodal, multimodal. Having a histogram and knowing how to construct the histogram will be of great importance and usefulness when you are trying to figure these things out. So again, I've just gone through and I've created all the histograms. This is something that we can do together in class with some data sets by using technology, because again, this is one of those areas where it will be most beneficial to use technology to create these pictorial representations as opposed to trying to do them all by hand. Several of them you could do by hand. It's going to be tedious. You really want to be as precise as possible, and the greatest degree of precision will come with the implementation of technology in your evaluation of the data. So the three examples that we've looked at the TV sets in a household, the number of days to maturity on short-term investments, and then we looked at the weights of that group of 18 to 24-year-old males. So I've created histograms for all three sets of data. The first group you see right here, that's the number of television sets per household. So the graph on the left is the frequency table. The graph on the right is the relative frequency. You can see that those two graphs look very similar in shape. The bars are the same height. So really, there's not going to be a huge difference. It just depends on how you your scale on the vertical axis, which would lead to maybe some discrepancies in the overall exactness between the two graphs. So for the short-term investments, you can see right here again on the left we have the frequency, which is the count of how many days it takes to maturity. On the right we have the relative frequency for the short-term investments. And then we also have the third one is the graphs for that show the weight of 18 to 24-year-old males. And then we have the relative frequency on the right. One thing I did neglect in the graph here on the left is I did not put the break in the graph. You can see that on the relative frequency. All that indicates, and that's something important, and you can use this little I don't know what you would call it, this kind of slash looking symbol, or you can use two parallel lines at an angle to indicate a break in the graph, and that just simply shows us that the graph is not to scale at that particular point. It doesn't go 0 to 120. The width from 0 to 120 is not the same as the width from 120 to 140. These graphs do have to be to scale in order to be accurately representative of the data that you are presenting. And like I said, I neglected to put that in the first graph. So I will have to go back and fix that. Hopefully I'll remember to do that before I post this on the website. No guarantees. The other thing I also want to point out is the difference in the graphs. One of the primary differences falls in how we label the x-axis. When we are using a single value grouping, the numbers that we're using to represent the each specific discrete value, we put it in the middle of the bar. So you can see 3, 2, 1, 4, 5, and 6. And that allows us to just see, so let's say we're looking at 5. The relative frequency for 5 is right here at 3. Same thing happens when we look at that was the frequency. The relative frequency for 5 is, that's a terribly drawn line, right at about 0.075 approximately. We have the exact values up on our table. When we talk about the limit grouping and cut point grouping, you can see that our bars cover a range just like they do on the table of values. So here we have 30 to 40 days to maturity, and we have this bar right here, and that appeared 3 times in our data set. Same thing is true for the relative frequency. Down here for the cut point grouping for the weights, our first value is 120 to 140. So we had that happen again 3 times in our data set. We had 3 males between the ages of 18 and 24 who were between 120 and 140 pounds. So single value grouping, your numbers line up in the middle of the bar, and this is important as far as the labeling of these graphs go. And then with limit grouping and cut point grouping, you have your lower value and your upper value on the left hand and the right hand line of your bar respectively. You can see, here's the word I was looking for, wave. That's what I used in my notes, and I said some squiggly line or slash. I don't know what I said, but anyway, yeah, use the wave or 2 slashes to indicate that the axis is not to scale between 0 and whatever your first value point is. All right, the next thing we want to look at are dot plots. They're pretty straightforward as well. You're really just going to have to worry about tallying up the values and then putting a dot representative of each individual value. So here with example 5, Stephen, yes, that's Stephen, is working on his man cave upstairs, and he's wanting to add a new Blu-ray player to his home theater system. Stephen's always investigating everything that he does, so anything that he does to his truck, it is not without exhaustive research on what's the best and maybe the most affordable upgrade to go with. So we're going to use him as an example and say that he is upgrading his man cave upstairs. So he looked around on the internet and he found 16 quotes on different brands and styles of Blu-ray player. The table that you see right here lists the prices in dollars. We want to construct a dot plot for the data. It's not difficult. Um, so our lowest value is $199. So here along our x-axis are the values from $190 to $230. And again, your scale can be whatever you want. I chose to go by $10 increments. So for $199, there is one instance of $199, and that gives me this point right here. The next largest value in the table, wait a minute, sorry guys, 197 is the smallest. So that's 197, not 199. The next largest value is 199, and there's three of those. So when I get to 199 on the x-axis, I put one dot for the first value, I put a dot above it for the second, and then another dot above that for the third, and that's all you're doing. You're just putting dots to represent how many times each value occurs, and then we would skip down through there. This again is going to come into play when we start talking about the shape of the distribution. Looking at this one, to me it would appear to be a bimodal distribution, because what we were going to end up doing in another section of notes is we would kind of imagine a curve that would fit this to some degree. And the reason I say that this might be bimodal is because it has two peaks. That's another discussion for another time, but that's just kind of giving you an idea of where we're going with this. So we would go through the rest of the data points and we would mark them all on the x-axis. The first point goes directly on the x-axis. The second point, if there is one of the same value, would go directly above that point. If there's a third point, it goes above that, and we would, and so on. If there's just the one point, you mark it, move on to the next data point. Stem and leaf diagrams are another useful way to represent data. Visually, you can see a lot with a stem and leaf plot. What you want to do, just if you look at this, how to construct a stem and leaf plot, the first step is if you think of each observation as a stem consisting of all but the rightmost digit. And then the leaf would be the rightmost digit. You write all the stems from smallest to largest in a vertical column, and then to the right of the vertical column you would put the leaves, and then you would arrange the leaves in each row in ascending order. So another case where example would help profusely in making sense of that. This table that we see here is the same table we had before for the number of days of maturity of the 40 short-term investments. If I wanted to create a stem and leaf plot of that data set, again I look for the smallest value, and scanning through here, I see 36 is the smallest, and then looking for the largest is 99. So let's just focus right now on any value that's in the 30s. So I have 36, 38, and 39. I do not see any other values. So looking back up here at the rules for constructing a stem and leaf plot, the stem consists of all but the rightmost digit. So if we look at the number 36, the rightmost digit is 6, so that means our stem is the number 3. Same thing for 38. The rightmost digit is 8, so that means our stem is going to be the number 3. For 39, the rightmost digit is 9, our stem is 3. And we have this first stem and leaf plot value set right here. So our stems are on the left, and our leaf is on the right hand side. So our stem is the 3, and then we have 36, we have 38, and we have 39. So we're putting all the rightmost digits in the leaf column. And there's always just going to be one digit represented in the leaf column. You're not going to do multiple digits. So like if it was 127, you would have 12 as your stem, 7 as your leaf, not 1 as your stem and 27 as a leaf. Because again, this, if we turn this sideways and look at it, it's going to give us another visual representation of the shape of the overall data set. This one would appear to be mostly normal and unimodal. It has one distinct peak in the graph. If we continue doing that, we would start looking at all the values in the 40s. So we have our stem is 40. We apparently only have one value in the data set that is in the 40s, and that is 47. So our leaf is 7. Then we do that for all the values in the 50s. So our stem would be 5, and our leaves would be all the values that would follow the 5 in any data point that has 50 something as its value. So we have 50, 51, 51, 53, 55, 55, 56, 57. Repeat that again for 60s. So 6 is our stem. 60, 62, 63, 64, 64. You guys get the idea. And we do that all the way up until the point we've exhausted all values: 95, 98, 99, 99. I've done this again with example 7, and this time we're talking about cholesterol levels for young patients between the ages of 4 and 19 years old. The average cholesterol level for age group between 4 and 19 should be 165 milligrams per deciliter. A pediatrician who tested cholesterol levels of several young patients in their practice found that many of their patients had cholesterol levels higher than 200. So that's well above the average expected value. What we did, or what I did with this is, so now we're looking at 3-digit values. So the stem is every digit except for the rightmost digit. So our smallest value here is 199. The rightmost digit is the 9 that's in the ones place. Okay, so 19 is our stem, 9 is our leaf, and you can see that here with this set of the first row. So then I would look at anything that's between 200 and 210. So there's 200, 202, 203, 207, 208, 208, 209. We do it again with 210 to 219 pounds. So 210, 10, 10, 10, 212, 213. And there's our everybody that's at a cholesterol value of 210. I think I said pounds a minute ago. I'm getting stuck on weights. But this is cholesterol levels, so it's milligrams per deciliter. And then the next one is 221. That was the highest value. That was the only one of its kind. So this is one line per stem. Then what you see on the far right hand side of your screen is 2 lines per stem. So what we might do is this first stem is 0 to 4, and our second stem is 5 to 9. Then we get down to the 200s, and we go 0 to 4, so that's 200 to 204. Our second one is 205 to 209. Then we have 210, 214, 215 to 219, and then 220 to 224, 225 to 229. So we've just taken the original value, and now we've broken it up and made it even more refined so that maybe we can see a better visual representation of what the data is. Is it normally distributed? Is it going to be right skewed, left skewed? Again, those terms will make sense later on. I'm just going ahead and getting you used to hearing them so that you can kind of expect what's coming next. So we didn't have any between 190 and 194. We had 1 at 199. Then we jumped to 200 to 204. We had 200, 202, 203. Then we jump again to the next subgroup, which would be 205 to 209. Then the next main group is 200, the 210s, and we break that down into the subgroups 210 to 214 and 215 to 219. You can see those right here. Then 220 to 224, 225 to 229. And we just add our leaves on there just like we were doing before. You could make the groups even smaller if you wanted to. You could have done, say, by twos. So we could have had 19 or 190 to 191, 192 to 193. But that wouldn't be as useful to visually represent what you're looking for. You just want to try to make sure that if you divide these things up into smaller refined groups that you are using something that's practical. It wouldn't be practical to do 190 to 191 and then 192 to 193. We would have a very unusual and large stem and leaf plot. That's it. Yeah. So in your homework set, yeah, right here, the first one tells you use single value grouping. Second one, single value grouping. Third one, limit grouping, tells you the class width. Cut point grouping. Cut point grouping. Dot plot. So that's just where you put the dots on the x-axis, and then if there's multiple values of multiple representations of the exact same value, the dots start going up vertically. Dot plot, compare, stem and leaf plot, stem and leaf plot with 1 line per stem, stem and leaf plot with 2 lines per stem. So 2 lines per stem is what we did on the last example, the very end of the last example where we broke it up 190 to 194, 195 to 199. There's going to be questions on this, I know. So don't panic. If you don't get it right off the bat, it's not a big deal. That's the whole purpose of us meeting together in class, is to clarify these things. These videos are just to help you as a guide, first to kind of get your little feet wet with what we're talking about, and then after that we can refine your understanding in class when we get together to most effectively utilize our time together in class. So go ahead, look over this. If you completely don't get it, don't worry. It's like I said, it's not a big deal. We're going to get there together, make sure that you guys are understanding all of this. These videos are not the end all be all of the instruction that you're going to receive. They are a resource. So you guys have a wonderful night. I'm sorry this video was so long. Just a lot to cover in this particular set of notes. So again, have a great night. I will see you all tomorrow.